Nice. All right. So this is like our Redshift architecture, right? Where you have these leader nodes, and then you have the worker node. And just remember that basically what happens is the leader node does like the planning, um, and then each one of the worker nodes will query its own data set, right? So here you can see we have this movies data set, and it's partitioned, right? So these are literally separate computers, and this is a computer too. But these computers, each of them have a partitioned data set, right? So you can see part of the movies data set is over here, some of the rows are 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 here. When we have a query, something like, find all the movies that starts with the letter D, okay? We can execute that query in parallel, right? So this node will query its data set, this node will query its data set, etc. So each of them kind of return the subset of the movies on their node that has the letter D, and then send them back to the leader node, and the leader node can send us, the user, all the collection of the results, right? It will combine the results and send it back. That also works with just like calculations, right? We talked about this before, that each node can query its data to find like the average year, and then it can send, the average from each of the nodes, right? Each data set, partition of the data set, back to the leader node, and then it can perform like a weighted average to get like the total average. And what's the benefit of that is it's faster. We get to perform these queries in parallel, which makes it quite nice. The other benefit is like, well, maybe there's, this leader node, it oftentimes has metadata about where, what data lives where. So if it's like, find, the Dunkirk movie, okay, that's fine. Find the Dunkirk movie. Well, it knows maybe not where Dunkirk is, but it might know, hey, the largest value in this partition is a C, and the smallest is an A. So you can just skip this partition because we know Dunkirk isn't in there. So there's kind of two benefits, right, of this. One is it doesn't have to look through all the data. It can just go to the eligible partitions, and two, it can perform parallel processing. All right, so this is occurring with Redshift. And then one tweak to it is that here I have the partitions, one partition per node, but we know that really the partition can be one for each core, right? Or CPU, one CPU can have like 4 cores, and so you can have 4 partitions on a single node. And so you can imagine performing this like we could have our data set partitioned 16 times over and have that, those 16 partitions be queried in parallel, and then send back the results to the leader node. Right? A benefit of this is that you kind of get this scaled computing power. So as the data grows, right, we're going to have to basically purchase more nodes, and then because of that, we're like naturally scaling our compute with the data. So you're avoiding kind of like if this was just a single computer, eventually it would get a bottleneck, right? Because it would be one CPU is kind of trying to do everything and query the entire data set. Here, each CPU or each core of data just gets its own slice or partition of the data. So that's why it's called like shared nothing, because this core, each core just gets its own data set and we don't have to share resources kind of across partitions of the data. This data set gets its own resources. Okay, so one benefit, I guess, in theory at least, of this Redshift model is you are scaling the compute along with the data, which was there to like avoid, overtaxing. Right? The idea is like, okay, kind of makes sense that these would naturally scale. That was the theory initially, but with Snowflake, the idea is, well, not really. We could have a lot of data, right? And have a ton of data, and maybe we don't need a ton of computing resources. So with Snowflake, it's this isolated compute. Just remember that. So basically what we're doing is we're storing all of our data in S3. It just looks like a database when you interact with it, but really the data is stored in blob storage, whether it's S3 or Google's equivalent. And this has zero computing power, right? You're basically storing this on a hard drive. And then we can have an EC2 machine, right? This is our data warehouse that then queries our S3. And the benefit of this is we can kind of have a ton of data here, and maybe we don't need a lot of computing power. And the data part, typically the hard drive is not the expensive part. The expensive part is, the CPU, the memory. Those are the expensive parts. So the downside of this Redshift model was maybe we're just getting more data, but we don't want to pay for the extra computing power along with it. In Redshift, you previously didn't have a choice. Now they have upgraded it, so I think you can avoid that. But this used to be how it was architected. With Snowflake, you don't need to perform that trade-off. You can have more data and scale determine the amount of compute that you want. And that could be either by, having, you can say kind of what resources you want on each data warehouse. You can make it larger or smaller, and you can scale the number of data warehouses you want. All right, so that's kind of what we saw. And then we saw, normally it's like, well, S3 is difficult to query. That's a downside of if you were going to store your data in S3, but, right, and by difficult, I just mean it takes a long time to read through all that data. But what Snowflake does is it automatically micro-partitions your data. So it will choose the columns kind of to partition by columns, and then we'll choose, the rows. So this way, when you query the data, it doesn't have to look through everything. That's where this services layer comes in, is when you perform a query, like find me, the movie Dunkirk, it will first go to the services layer. The services layer has information about how the data is partitioned, and then because of that, it only has to look through a subset of the data to basically retrieve back the result that you want. Okay, so this is like the main, we went through other things, but this is the main benefit of Snowflake, right? Is that one, it's cloud-based, right? Meaning this is just an EC2 machine, this is just S3, so it connects directly to your cloud, or to the cloud. And then two, that is isolated compute, meaning, the amount of data you have doesn't determine how much computing power you have. You can just say, hey, I don't need this, and just turn it off. Okay? Any questions about that? Cool. Okay, so let's get into Spark. So as we'll see with Spark, the main difference is that actually, we try not to store data on disk. By default, data is just not stored on disk. In Spark, it's stored in memory. So, this is kind of what I say up front. Normally databases, now I can start downloading it. We do both storage and processing, but Spark, it just focuses, or I should say, Spark just only uses memory and focuses on processing, not long-term storage. So how would something like that, and then I'm just doing some initial setup. So I'm importing the Spark library here. You can set this is the name of your database essentially, films. And then I'm saying where this database lives. So this could be a URL. Remember, with AWS, this could connect to an RDS URL. Here I'm just saying local. Right, so I'm not using an AWS cluster, but that's what this could be if you wanted to boot up an AWS cluster. And then here I'm just passing through this configuration object that's right here, this films database, local, passing that through here, and then saying, okay, this is kind of how I'm going to connect to this cluster is through my Spark session. All right, so this is kind of same kind of thing as the setup that we do with SQL Alchemy, right, or Scicop G2, right? We might say what is the URL we're connecting to, whether it's local or on RDS, what's the database we're connecting to, and then we have that get DB or whatever to then actually interact with the database. This right here, all I'm doing is I'm literally just reading in data from S3, and this is just a data frame right now. And then here, I'm passing that data frame into my Spark cluster. Okay. So I do spark.createDataFrame, and then movies.take1 just gives me back that first movie. So you can see that here. I'm kind of rushing through this. How do you interact with it? Because it's like I don't have this memorized. If you think I do, you're wrong. I just like copy it every time, right? So this is just like some initial setup, and then here this is really the only we're just selecting the first row at this point. The important part, like I said, is more conceptually how everything works. So what I'm trying to show here is that for long-term storage, think about what we just did. We pulled our data from S3. So this is like totally isolated, right, from the Spark ecosystem, right? Like this is just a data lake. It's just data that we're storing. And then we can decide to, boot up a Spark cluster, read that data in. Here I'm doing it with this, I'm using pandas to read it in, but there's a Spark method, spark.readCSV, read.csv, to read in that data directly to Spark, okay? So the idea is the long-term storage in S3 is isolated from your Spark computing, okay? What we're doing right here is we're then reading the data from S3 directly into memory and storing the data in memory. When you want to search through the data, it will also use some memory for, say, if you query the data, it will use some memory for querying the data, and also obviously use some CPU resources, right, to figure out how to query it and actually perform the operations. So this is kind of like and this, you see this is showing the same thing, right? Store the data kind of outside of your Spark cluster long term, read it in, and then notice what we're doing is, here I'm just showing it with one computer, but really this could be a cluster of computers. So even if you have like an enormous data set and you're like, how's this whole thing going to fit into memory? Well, we can boot up a cluster of computers and partition the data across these nodes. All right, so that's what I'm showing here as we have, Dark Knight and Dunkirk here, and Michael Clayton over here, and then Pulp Fiction down here. And then just to hammer home the point, you can contrast this with Postgres, right, where its storage is directly, in the exact same location, right there. We have a hard drive for long-term storage, and we also have, our CPU for processing it. So the difference here, one thing you can think of is that Spark is like what they call like a query engine, as opposed to storage, and I would put like long-term storage. I think there's a better word for this here. I just can't think of it right now. But Spark is primarily concerned with being a query engine, right? It's just there for querying the data. So when you think of Spark, the first thing that you can think of is just that the data is stored in memory, and then it uses memory and CPU to process the data. And we get some benefit. And for long-term storage, we do not use Spark for that, right? Why? Because we don't want to, memory is expensive. So in a cluster of computers where we're relying on that memory is expensive. So we're probably going to shut down this cluster when we're not using it, and then just still have our data stored in our CSV file, right, in S3. So what's the benefit of this? One is kind of what I said, it's relatively cheap, right? Because we're not relying on this for long-term storage, we can shut down this cluster. This is just a hard drive. So it's cheaper for us to have long-term, have this storage be in S3. Another benefit is, if you think of how we are able to just query our data, how quickly we could do that, right? This is a different process, if you remember, than when we're doing something like Postgres. Because with Postgres, we would need to, first create a table, right? And then we need to take the data and transform it, right? Say, oh, this should be an integer, this should be a date time, right? These columns go here to fit the data into those tables. So with Postgres, we're basically performing that ETL step, right? Where we're transforming and then loading. And we have to know something about the data to figure out what tables belong where, right? So you kind of have to do some exploratory analysis, figure out, do some data modeling, right? Create the tables, load the data into those tables. Here, we don't know anything about it, right? We just read this CSV file and create a data frame. And then we can explore and coerce from there. So this is really like an ELT process, right? The data is loaded. We read the data into our Spark cluster, and then we just get to work and start performing our transformations. So this is why Spark oftentimes people use it for like a lot of unstructured data, meaning like text data. So an example of that would be like reading log files, right? It's like these log files are messy, but there's a lot of them. Maybe they're just stored in like S3. So I don't want to do the work of like transforming this data all up front. So we can just read the S3 and let's start exploring it, right? And also I get a cluster of compute, so we can deal with a lot of data here too. There's a couple questions. On a single computer, these clusters won't be performed like partitions to offer parallelism. Yeah, these in Spark, you can partition it one partition per core of CPU, just like in Redshift. So it's not one partition per node, but one partition per core of CPU. And then materialized view. Remember, like a materialized view is actually storing the transformation on disk. Here you're not storing really anything on disk. You're just directly reading in. I'm not quite sure. Maybe you want to expand on that, Conwell. But you're just directly reading it, and then you can just kind of get to work on your data. The same thing as you might do in Pandas or SQL from there, but you don't have to create a table first at that point.
Yeah. Correct me if I'm wrong. My understanding is it's sort of caching, like because there's hard drive, we create an engine for that. And then you mentioned that we are not essentially accessing the hard disk or the Postgres database. We are, from now on, the moment we create an engine, from now on, we are accessing these clusters for all the operations we want to perform. So if I want to do a write operation, my understanding is first it will happen on the cluster and then it needs to happen on the actual data as well. How exactly that is performed?
By default, it won't try to store data on disk. It really just does that when you can force it to. I'm sure. Like I don't normally, but you can force it to save data on disk. So it's not saving data on disk by default. If it runs out of memory space, it will save some data to disk, but it tries not to, because it takes time. Those read and write operations take a good amount of time.
Yeah. So in general terms, is it sort of a cache? I'm still not able to understand what exactly is Spark. Then, like, is it a way of accessing data faster because it essentially fetches the data into the memory instead of.
Well, yeah, it's a lot faster because these computations are not really written to disk. Everything's in memory. It's in parallel. It's the query when you have a lot of data. It's quite fast to be able to write queries, perform those computations, like either any pandas kind of work that you would want to do or SQL queries. It has interfaces for both, and you're not, it can read this relatively quickly. The data stays in memory, so then you're not reading the data again from disk very often. It just lives in memory, and because of that, the expensive part oftentimes of a database is the reading from disk and writing to disk, and that's getting avoided here.
Yeah, but that's exactly the question I have. Like, if that is the case, any real time, actually, Kyle also mentioned something in relation to that. So my question was, will get more clear from his remark over here.
Let me see.
So when it comes to real-time operations, any write operation on the original database, or we want to actually do a write operation, if
You're
that
not you're
is
not
something
really doing. I mean, you would write the data back to S3 when you're done.
directly to S3, not through Spark,
I mean, you can write it. You can do Spark dot like write, and that data wouldn't save here. It would be written, at least as far as I know, it would be written directly to S3. Maybe there might be some, but yeah, the data would just be written to S3.
I just Googled it a little bit just because I was curious, and it seems like because of the like parallelism, it's a good choice for real-time streaming of data. I think fraud detection is one use case, but
But
I
that's
think I'm
Spark
picking up.
streaming. Like that's Spark.
Sorry.
That's Spark
Yeah.
streaming. When you have like a lot of data that you
Hmm.
want to query kind of like in parallel. It could be unstructured data, right? So it's like basically like the first thing is just think of, okay, what do I get by being in memory, right? So we kind of talked about, I mean, it really is like a lot of these things, right? Like you get schema on read, so you don't have to create tables for it to just get started and working with it. A lot of the queries are faster because you're not reading from disk. You're only reading from disk right here, and then you're done. It tries to avoid in the computations reading and writing to disk, where other databases don't take advantage of that as much. So because of that, the queries are just performing the query and get a result. Like that's a lot of what you do when you work with databases, right? Is you just try to see what's the result of a query, not necessarily saving it, but just get some information, and then you can always write that if you want to save it or cache it. You can write it back to S3. But if you think about it, like oftentimes you'll be writing back like a subset of the original data, or you're not doing this very often, right? Like by very often, I don't mean once a week, but maybe you just do it one out of every 30 of your queries. Maybe at the end, when you're done, then you write back to S3. So maybe once an hour, or once every 30, 40 minutes. So, that's saving a lot of time. If you've worked, like I've worked with, even if you use like Kaggle and you start working with like some of these large data sets, pandas can be very memory intensive. So even just doing like pandas like filter for these rows, you're doing it across the entire data set. I've waited, and like my students when we taught data science have waited like 10, 15 minutes just to do like a simple like filter operation in pandas on a single machine, whereas you can do something similar in Spark and it's like a couple seconds. All right, so that's the big innovate, like the reason why a lot of practitioners will use Spark is simply because it's faster, and it gets that speed by being in memory. The third kind of benefit that you get is what data scientists, right? Like use Spark all the time, and the reason why is because you get stuff that you don't get with a typical database. Meaning, like there's like a PyTorch library in Spark that you can use. There's a lot of like these other models, like for those of you who know some data science, like simple regression models, tree-based models, right? Like random forests, things like that, like the sklearn type libraries. You can perform those operations in Spark, and so if you think about it, that can occur, parallelized, across a cluster of computing, and they have to hold, this goes into how ML works, but it has to really hold those computations in memory in order for it to occur. And so being able to do this in parallel and hold all that information in memory is very valuable, right? So, that's the reason why like a lot of data scientists will do something like this, will use this, is because it can take hours, or depending, that's even like days to like train an ML model, and we, as with like these LLMs, right? That's a whole different story. But even like a simple, like PyTorch style model, right? Deep learning model can take a long time to train. Even something like XGBoost can take, depending on the amount of data and what's occurred can take some time. And so the fact that this will kind of, we can scale up the amount of compute and memory that we have in a cluster can be quite helpful. Let me see. Okay. In terms of speed, wouldn't Cassandra be the best DB? Because, okay, so Cassandra is mainly used when you have to, like, I think I'm thinking of the right thing. Yeah, it's mainly used with, like, fast, is more with like customer facing data. I can, like, we can look more at that. I think we have, I think we have some stuff on. I forget if we have something. You know what? It might be some. I might have to look at Cassandra. I might be thinking of a different database, but Spark is mainly used as like an analytics. Is really used like as an analytics database. And like I said, you can think of it like for data science, and then also just for performing analysis relatively, with a large amount of data, it can be relatively fast. One thing to keep in mind is like these databases are always, they're competing with one another, like these analytics databases. So like Snowflake is still also quite good for a lot of data. It just isn't purely in memory. So it's gotten a lot better, or it performs quite well. Spark has existed, before Snowflake, and it was like was quite fast and was like the go-to option for, working with large data where you care, where these queries might take a long period of time. Now, in terms of Spark, one thing that it's still quite good for that. Other databases can perform well. It's still like, for data scientists, it's great because it has these built-in libraries that we're not losing. They're not kind of like these. They're quite good in terms of the data science algorithms, and you can train a large amount of data on it, and have the model, and then be good to go. So, like I said, like it's hard to say like, data, it's in terms of comparing it to other databases. That's a detailed conversation, and like there's always more. Databases are always competing with one another, so they always kind of get better. But this is kind of the advantages of Spark, and this is how the architecture, the fact that it's in memory, allows you to do kind of these few things. All right, so cheaper storage, kind of this ELT approach, right? Memory intensive computations, right? And just like fast queries, right? Because this is performed in parallel and avoiding writing to disk. Cool. One good thing to do, by the way, is like you can literally, for like this database versus that one, I literally ask like ChatGPT or look at blog posts because, there's so many different kinds of databases, and the differences between some of them can be so slight that you just kind of have to do your own research a little bit, or oftentimes to figure out exactly the scenarios in which one is better than the other. Okay, so this is one thing, is just like Spark, is saving, this data is saved in memory. It's not saved on disk. And then, it's you get these computing resources, to perform the analysis, right? To have these queries, or to train ML models or explore data. The other thing is just, and this just goes into some of like the architecture, right? As we kind of alluded to, Spark does have like MapReduce. Just to kind of put names on, the different nodes and things like that. This is the equivalent of like our leader node. It's called the driver. There's this Spark context, which is what you'll like connect to. So you can see like when you see that we are having this get or create connecting to this cluster, this SC stands for the Spark context, and that's part of the leader node, right? And then, as we talked about before, the amount of partitions that you have, that depends on the number of cores per each node. So if you have 4 cores on the CPU and 3 on each CPU and 3 different nodes, you get 12 partitions of the data. One other thing to note is, right, this is called a node, but you'll also often hear people refer to this. It's called a worker node, technically, each of these, but you'll often hear people refer to it as an executor. Executor is technically like the software running on each node. Like you have Windows running on this, on each node, So people will say like 3 executors, and that's the same. Basically, it's the same kind of thing as 3 worker nodes, right? The node is like the computer, the executor is the hardware, but it's not 1 per core. There's only 1 executor per each node. All right, so you'll just hear that when you work with Spark, right? In the executor, you can see, right, that I'm showing you what it consists of. The CPU, the processing power, the memory. The memory is split typically 50-50 by working memory and storage. So storage, this is like where your data set lives, right? Your data set, your partitions live in memory, in storage. And then the working memory this is where, like I said, it tries not to write to disk. So to the extent that it caches any information, it's storing that in working memory. All right, it's trying not to write to disk because that's slow. It doesn't mean it doesn't happen, but it does that more for a spillover when it runs out of memory, and instead tries to just save any results it needs in working memory. All right, which is it's just dividing what it's using this memory for. And then, as we know, like just to show you, right, it will by default perform your queries in parallel. So I do scc.parallelize movies. SC is our Spark context, right? And it reads in a list. This creates an RDD, which is kind of like the main data structure that you're working with, is this RDD, which stands for Resilient Distributed Data Set. And you're skidding the first part, which is that it's like distributed, right? It's distributed because this data set is partitioned kind of by default. And then if you look at it, you can do movies RDD, get number of partitions, and you already automatically see that it's 2. And where did that come, like why is it 2? It's 2 because when we set up Spark, or if we get all the code we've worked with so far, it's really just this. Okay, we said, hey, I'm using localhost, and this is the number of cores that I'm allocating. Okay, so 2 partitions, 1 for each core that I'm allocating on my computer. Okay, so you can ramp this up, but this is good for now. So by default, right, it's just splitting the data in 2, and then when I use this like movies RDD, you can see I'm just gonna look for the match for Captain Marvel, and then give me back all the results at the end. Okay. Yeah, and here I just kind of talk about what I already mentioned. By default, it's 50% working memory, 50% storage. If it runs out, it will write to disk, right? If it runs out of memory, of like working memory, it will write some of the results to disk. Like let's say it's looking for all the movies that begin with the letter D. If it runs out of working memory, it's going to write some of those to disk, which will take time and then read back, right, to disk. If you're training a model, it'll save some of the results, I'm guessing, to disk, and then read it back to memory where it needs to. And that reading and writing to memory is like the innovation that is trying, especially at the time, is what made Spark so fast. So you are trying to avoid that reading and writing to disk, and it tries to avoid that too. All right. So this covers a lot of what we were talking about. The idea is just that we partition our data. You get that kind of by default by saying how many cores you want to allocate, you want to use in your cluster. Okay. And then we just do sc.parallelize. That creates for us that reads in our data, creates this RDD. This RDD is, you're always working with an RDD. It's basically like a pandas, it's like the equivalent of a pandas data frame in the sense that it is kind of like the object type that you're working with always. And, then you kind of operate on it, okay? Even here, like before I do .collect, it's returning a different RDD, a Python RDD, but this is always a data set. And then finally, we want to see it, so it's just returning finally a Python list. But it's always basically, you're always working with this. The other thing, like when you do this map reduce, Um, one thing to just be careful of is shuffling. So I'm just doing some initial. I can walk through this in a minute, but just conceptually, for right now, we have our list of movies, and we are in this case we're going to. Here I'm specifying the number of partitions, so I'm saying there's 4 partitions, all right, of the data. Even though I wonder how many cores I allocate. I only allocated 2 cores, so really, it's more. It won't parallelize this beyond that, right? Because it can't perform more than 2 processes simultaneously. But just like for this example, I told it to at least try to partition across 4. Okay, so same kind of thing, right? It's going to do this map reduce. If we say like find Michael Clayton, it's going to, we know our data is partitioned, and then it's going to look for the movie Michael Clayton across each one of these. So that's the map operation. That works fine. What we want to avoid, I'll have to get into this in a second. What we want to avoid is this thing called shuffling. I might have to do this real fast. Sorry, I'll explain what I'm doing in a second with this auth token thing. Okay, so what we want to avoid is this thing called shuffling. So let me just explain we talked a little bit about shuffling, but I just want to explain like how it occurs. So like I said, we partitioned our data 4 ways, right? So imagine part of our data is here, part of our data is here, and part of our data is here. And then let's say that we want to, you can see I'm performing a group by each movie's first name. So the end result ultimately that I'm getting is this, right? Letters M, these guys, letters S, these guys. This group by often leads to shuffling. So if you think about what Spark is going to need to do, is the first thing that it's probably going to do is, remember, these guys likely, if we're partitioning it, they're likely to live on different nodes, right? And so Minari lives on a different node than Michael Clayton, right? Meaning a different computer. So what we're going to have to do, what Spark's going to have to do when you do this group by, is first collect everything with Minari together. All right, so it's going to be like, all right, well, partition 1, maybe it starts with Shazam and Minari, but I want to change it so that we send Michael Clayton over to partition 1, right? That's why it's grouped with Minari. And then partition 2 will get all the S things, so that would be Shazam and Sicario. Okay? And then, so you can kind of get the point, is partition 3 might get each one of these. Now what Spark is literally doing is it's taking the data. The first step it will have to do once it sees this group by is going to have to take the data, which lives in various nodes, right, different partitions, and group them together. And because this data can live across different computers, sending the data from one computer to the other takes time, right? Here we have like 8 records, maybe not the biggest deal, but if you imagine the amount of data we might be working with, right, like that's called shuffling. That sending of data in between nodes can become very expensive, right? So that's something to be aware of. There are techniques. I have some notes on some techniques to avoiding it. You can kind of imagine how you might avoid shuffling. It's like partition based on how you're often, querying the data, right? To make sure that shuffling's not occurring. You can perform a filter before you perform the group by, if possible, to reduce the amount of data. Things like that. Yeah, Conwall?
Yeah, why would we do the group by afterwards? Like, if we want to do the partitions according to our choice, wouldn't we do that at the time of creating the partitions? Like where we mentioned we need 4 partitions or whatsoever it is, and then also specify the group by according to this lambda.
Well, you can
Like
repartition. You might choose to repartition the data, but you don't know how, that's going to take some, that's going to also involve some shuffling to repartition the data. So you want to kind of, which you might just have to do, right, is repartition the data. But if you can, when you choose the partition on a column, right, that you're often going to be like querying on, or that's going to, that you're going to be grouping on, right, then you can avoid this degree of shuffling. But like your queries are going to change, right? You're going to have different kinds of queries. So sometimes you might want to group by one thing and sometimes by another. Right? So it's like, it's just to be aware of like, because you're working with a lot of data. So, so the shuffling can really be quite costly. And so, and the other thing is like, oftentimes you're tasked with like, how do you optimize these queries? So the first step is just knowing like where things can go wrong. And that's essentially what's going to go wrong is shuffling. And that I guess there's a couple of ways that occurs. One is with this group by. The other thing is joining, right? Right, because joining also, if you join together different tables, you literally are, moving columns from one table over to columns to join with columns in a separate table. And so if one table lives over here, right, you're going to have to copy that or move that data over to a separate node, right? And that can be quite expensive. So it's the moving of data from one node to another that takes a lot of time. That makes sense? All right, so it's like same thing with join. What can you do? Well, there's different kinds. You can specify joins. There's something called like a broadcast join, where you can take the smaller data set and make sure it's the smaller data set that's the one that moves to each node and not the larger one. So that way you're moving less data, right, in each case. So if it's just like a data set of states, right, there's only 50 records that you're joining on, say, each customer, right, that's going to be a lot cheaper than the other way around, than taking the customer data and moving that to where the states are. But like, it's not always the case that Spark is smart enough to do that. So you can specify the kinds of joins. You can reduce the data before you're performing the joins. You can repartition the data right beforehand, or partition it based on. This won't work for joins, but with group by, you can partition it based on how you're grouping the data. That way, like the G's are all together or whatever. The 1990, if you're grouping by that, all of those are together. So, and you can repartition the data in Spark if you're about to then perform this operation a good amount. All right. So it's something to be aware of, and then you can Google, and then I gave you some techniques of how to improve it, but there are more than just that too. One thing you can see, this is what I'm doing up top here. I can now walk through this, is showing you guys what's called like the Spark UI. So here I'm installing PySpark like I have before, and I'm also installing this thing FindSpark, which they just told me to do, and then this Python ngrok is a way to I'll show you. It's kind of this also. There's a similar technology called local tunnel, where basically the whole issue we have is that there's like a Spark UI. Let me just see if I can show it to you. I'll show you what it is. So we can go here. All right, and I'm going to do visit site. Okay, so this is my Spark UI. If you're working with it, and let's take a look. Can I refresh? Oh, hold on. Let me actually perform some jobs. Map reduce shuffle. Spark RDD parallelize. Let me actually do some stuff. Okay, so I'm actually so I just executed this. I'm about to execute this, and then let's do one more. Group by, and then collect. Cool. And now let's refresh. These are my jobs. Okay? So you can now see each of the operations and see how long they took, right? And then what actually occurred underneath. So for instance, this is my most recent job, which was this guy right here. Group the movies by their first letter. And you can see how this occurred. So I click on it. You can see it had these two stages, right? The group by and then the collect. So it grouped by, and then finally we had this collect, which is like show me the results. Now, if I look at this, we can look at the group by. I think it's here, event timeline. Okay. It's very slight because we're doing with such little data, but this is the shuffling. These slices in yellow. I wonder if yeah, you can see it, shuffle right time. Okay. So here you can see, right, it had to send the data. It's also, we're only using one computer, so it's very cheap in this case. But if this was distributed across multiple computers and a lot of data, this would really expand, right? And this can become quite expensive. So this is what we would want to look for and to avoid. And right, this is kind of this is occurring because we called a group by, and it had to send data in between partitions, right? I had to collect my G's together, put them together, and then put them on a list and perform that component of it. So again, like, what are some techniques we would want to do this? Partition it, properly. You also want those partitions to be relatively even so that shuffling doesn't occur, in one node quite extensively, right, which you're going to have to wait for. You could try to filter the data beforehand, right? And then again, like we talked about joins, choosing the optimal join for that. So here you can see this. Now, this was actually a little tricky to see this Spark UI and connect it with Google Colab is a little tricky. So let me just walk through, and the code's here for you, but I just want to explain a little bit what I'm doing. This tool, the issue is that Spark UI ideally is, you can see it here, is that you can like click here and get to it, but it's not, this doesn't exist, all right? So what you have to do is, because this thing is supposed to live on your local computer, that means in this case, because I'm on a Colab, it's like it lives somewhere on my Colab. But it's like, how do I don't get to a website on my Colab. It doesn't know how to do that. So instead what I need to do is use this technology called ngrok, which is setting up a link from, this is the Colab's local host, their UI port, which is 4050, or this is where this Spark UI lives, and put that to a public tunnel, so that this is a website that lives, like anyone could access. You guys could access this too. You just need basically the right password to do that. So that's kind of the other component of it, is it's now putting this on the public web from my local computer, and then I'm accessing my Spark UI. All right. In order to do this, the only kind of tricky part is, you saw I had to put in my authentication token. All right. And I get that from this ngrok website. So what it will do is it tells you enter your authentication token, which can be copied from this link. So you'll kind of run this code. You'll click on this link. This will ask you, let's maybe go to a different thing. This will ask you to, create a new account, right? So maybe first create a new account. You enter that, and then after you create it, then just re-click. Just go to this. Just go to this link, and you'll get your authentication token. All right, and then you just copy this, and then it asks you. It asked me to enter it here. So I literally just copy it and then paste it in there. And then once I get that, then it gives me my ngrok tunnel. And then I click on this link, and then from there I can see my various jobs. Okay, just to go through that again, right? So basically you're seeing 3 different jobs. There's one job for each. Every time you see results, right? Like every time you actually see, like here I see some results. This is the first job, okay? And you see that here. You'll see them in reverse order. So the oldest one is right here. This was number 0. Then came the next job. And then finally came that last one. And then you can click on the job that you want to inspect. And then this job had 2 component, what's called stages. 2 stages, part of them. The group by and then that collect here. And then I can click on the group by if I want to look at this a little bit more. And by the way, notice. I'll go back for a second. Notice that it's highlighting for me. Well, how long did it take for shuffling, right? Because it knows that this is kind of what we want to optimize: shuffle read and shuffle write. Okay. And then you click on, the stage, and then from there you can see what was the shuffling time. You can, in terms of, you can see four. This kind of, stepping on something later, but you can see there's 4 tasks. The reason why is because we have 4 different partitions. So this stage, remember, is happening in parallel. These steps are happening in parallel. They're happening across each partition simultaneously, right? And that's what this is displaying. How long did it take for each one of these partitions to occur? And this is valuable because let's say one task is taking like a crap load of time. Well, that means maybe I should repartition my data because I want these to be relatively even, because I don't want to be waiting on one partition a long time while others are done relatively quickly. All right. So the more important thing, I think, again, is like just understanding a little bit about shuffling, how it can occur, and then there are these various ways to try to prevent it, right? So you can kind of look for it and then try to avoid it if it becomes an issue. Questions about that?
I have a quick question regarding shuffling. But that emanates from the source, essentially. In this lecture, we are taking S3 bucket as a source. So I understand when you mentioned that when we write to Apache Spark, that is something which will happen very rarely and totally understandable. But when it comes to the data source, that has chances of being updated very frequently, like the S3 bucket in this regard. And once we create the engine for that, my understanding is, and please correct me there as well, that this set of clusters will not be updated with the data which was updated in the S3 bucket once the engine has been created.
No, it can be rewrite. You can reread it in there. And you'd have to reread it, but yeah, you can.
What do you mean by that?
When you in order to read this data, you can kind of see it here, right? We're reading the data in from S3. So you can reread in the data from S3 into your data frame.
But here so that's the point. But how do we know?
Well, the data is not gonna. I mean, you're performing kind of like offline analysis, more or less, right? So it's like you don't. You could deal with like, okay, this data is ready to. It's kind of like fairly static at the moment. This is the data that I want to perform analysis on. When it's analytics, you don't want to have to worry about changing data, right? Like if I'm training an ML model, I want that to be fixed. So you could store this in a folder or just a file, and then just not change that. You only are performing analysis on this folder or file. It doesn't mean you don't have other data. Right, you can have other data, but then this is the data that you're performing analysis on. Right, it could be specifically for, like your analytics essentially. Right, like you can, right, the same way that we would have different we would have raw data in DBT, like our raw tables, and then we would have the data that we're performing analysis on. The same kind of thing here. We could have our raw data that's maybe getting updated more frequently, and then copy over certain data to a different folder, and that's the data I'm now going to perform analysis on.
Okay, one more question though. Assuming we need to run the script every day or so, this the one in the cell. So the question is regarding shuffling that. Is there a possibility that addition of more records in the data source, and based on the partitioning strategy or something, that leads to shuffling somehow within the clusters we have defined for our engine, Spark engine?
Well, yeah, I mean, like you can imagine we do a group by, but there's only letter A data, but now we add in the B's and the C's, right? Like Well, yeah, now there's like, as the underlying data changes, then there could be like more shuffling that occurs. And it doesn't mean like, I mean, but it's going to occur, What I think what you would do is you look at take a sample of the data, run the query, see where the shuffling is occurring, and then try to optimize it, and then kind of assume that hopefully your data, you're going to have to check for drift, but your data stays in a relatively similar distribution, and then see, as long as you're reducing it on on that sample of the data, it should be mimicked, when with like live data or with data that's that's continues to be updated. Yeah, but typically, like when you perform this analysis, you want it to be reproducible lots of times. So you don't want oftentimes to work with live, ever-changing data, because then people are going to be like, well, how did you get those results? And it's like, well, the data changed, so we can't debug it, Like you want to probably read in some of the data at this timestamp, save it into a different folder, and then just work with that folder. Right? Or you can work with data from a specific day, but you want your analysis to be reproducible. So you don't want to say like, oh well, the data changed, so of course my results are wrong now. You want people to go back and be able to check your results. Typically,
I was thinking about a running analysis, like this might be.
Yeah, I think you keep thinking about streaming data, but we're not really talking about that right now. Yeah. Cool. All right. Okay, so that's pretty good for now. So let me publish this. Again, I think a good